We'll talk about slightly different form of a neural network called a convolutional neural network that is typically used to process images. We use the fully connected neural network for the MNIST dataset, and what fully connected neural network does, it takes each pixel and then assigns a weight to it. So it takes a weighted sum of each of the pixels. However, in real images, if you think of an image, let's say you have a image on the beach, right? So what will happen? You'll have part of the image that has a sand in it, and part of the image that has ocean, and part of the image that has person. So it has a person in it. So that's your typical image taken on the beach. And if you basically look at this ocean part of the image, right, and you take any pixel here, then the pixel in this ocean part of the image is going to be very similar to pixels around it. Very similar to pixels around. So they're all going to be bluish color. Okay, and then the same for the sand. If you take a pixel from the sand image, then the pixels around it are all going to be very similar. So there is no real reason to treat each pixel individually. And the convolutional neural network tries to solve this problem by treating them as groups. So here's an example of the fully convolutional neural network, and we're trying to analyze a 200 by 200 image. So we need the 40,000 hidden units, a lot of the parameters. So we need to weight each of those pixels. So that's a lot. Instead, what convolutional neural network does, it does what is called locally connected layer. So essentially, you will take an image and you process it block by block. So instead of processing pixel by pixel, so this is a block, and the block usually, for example, 8 by 8 pixels. And what you will do, you'll take a weighted sum of those pixels, and then you move to the next block. And then what you do, you take a weighted sum of pixels in the next block, but you use the same weights. So every time you take a weighted sum, you use the same weights. So instead of having the weight for each individual pixel, you only need 8 by 8 weights. So 64 weights is required to process the whole image. And that's basically the trick how you can make the model to have much smaller number of the parameters. And that's how it's shown here. That's the convolutional neural network. It does it block by block. You can think of it as a sliding window, and you take a weighted sum inside this sliding window, and you keep doing this until you reach the end of the image. All right. Another thing to keep in mind when you process images, that you have to have a lot of computing. Those are very computationally hungry tasks, and the TPU, tensor processing units developed by Google, is one of the accelerated CPUs or processing units designed specifically for images. Essentially, if you think about what you need to do when you do deep learning, is you have to calculate those weighted sums of the pixels, for example. And this is a called linear algebra operation. So it's a matrix vector operation, matrix vector multiplication, or matrix multiplication, the more general form of it, matrix multiplication. So that's the main computational task when you do deep learning, and TPUs are designed to do this matrix multiplication very fast. So nowadays you rarely would do image processing using your laptop CPU. You would typically use those specialized processes, or another processes is GPU, graphical processing unit. That's what gamers would use to accelerate the graphics of the game. Essentially, when you try to generate graphics, it's the same operation of the matrix multiplications that is used, and NVIDIA is one of the leading companies in processing those GPUs. They figured out that, okay, so actually for neural networks, we have to do the same operations as we do for generating the graphics. So analyzing images and generating images is the same type of operation, so we can use GPUs to do deep learning, and they were successful in doing that. And if you look at the presentations from NVIDIA from the last few years, essentially they're now claiming that the deep learning company more than the gaming company, although still a large chunk of the revenue comes from selling chips to the gamers. Yeah, in China, you can click to the video link and see how Chinese schools are prototyping systems to monitor fatigue levels and attention levels of students in schools, and they use those bands on the head, which basically monitor the brain activity, and they also use video cameras, and all of those things are analyzed by neural networks, and then at the end of the day, teacher will get a report for each of the students. And some of not very nice uses of artificial intelligence is this sense face used by China to profile Uyghurs. It's a Muslim minority. They speak Turkish type language. They're very close to people from Uzbekistan or Turkmenistan, so they're not Chinese, and they are Muslims. And for several years, Chinese government is treating them in an unfair way, and one of the ways they're doing is monitoring them. So here you see an example where each Uyghur, this is entrance to a bazaar, to a market, open market. When they enter the market, each Uyghur has to go through this photo detection, and the photo detection tries to identify whether this specific person is in this database of people who have been searched for or not. Another example for cosmetics, again, analysis of your image and try to tell what's your quality of the skin on your image, the moisture level, and the pores. But another example of generation, so instead of classification problems, so far we saw examples of classification. So you have an image and you try to classify, meaning you try to identify what type of object is shown in this image. This is another task when you basically generate an image. So you have a generator, and generator outputs an image. And here's a more practical example. One of those models doesn't exist. So it's used in the advertisement campaigns. Instead of using the actual faces of people, you can generate those faces now, and you can use them in your images, so you don't have to do photo shoots, you don't have to pay the model, you can just generate the model nowadays. Here is one of the funny ones. AI generated artwork was sold for almost $500,000. And actually the code to generate those artworks was written by a high school student from West Virginia, and he published it on GitHub. He made it publicly available, and a group of 3 people from France, I think, downloaded the code and generated this artwork. And here they signed it using the formula that was used for the generation, and they sold it actually for almost $500,000 in one of the auctions. Same idea. NVIDIA had this project where they tried to generate Rembrandt. So you see here 4 different paintings or pictures of the paintings of Rembrandts, and one of them is fake. One of them was generated by a computer. So generating algorithms became very powerful, and sometimes you have hard time distinguishing which one is true and which one is not. It's not only images that can be generated using artificial intelligence. Google had this little project where they can generate music, and they claim that they can generate Bach type of music. They took all the works by Bach and they tried to analyze them, and then they predicted, tried to generate the new ones. And a friend of mine who is a poet, he claims that poetry nowadays also can be generated using neural networks, and it's actually would pass the standard of modern poetry. So you will have hard time distinguishing human written poetry from the machine written poetry. But let's maybe look at more important examples of image processing. We're back to the problem of classification, identifying skin cancer from an image. Google Virali is the healthcare unit of the Google. They had this data set of 130,000 images of skin, and they had 2,000 different diseases. So those are the number of the labels. And essentially the task is to take an image and predict y, and the y takes values 0. Let's start with 1 so it's easier. 1, 2, all the way to 2000. So it's logistic regression with multiple classes. And then they had the test data set, 370 high quality biopsy confirmed images. And they were able to show a better performance than 23 of Stanford dermatologists. And you basically spend 10,000 hours to train the deep neural network. On modern computers, it can be done very quickly, and then at the end, you can outperform a human dermatologist. And let's actually talk about this example, diabetic retinopathy. It's a major disease that leads to loss of vision. And usually this disease, it can be diagnosed early, and if you diagnose it early, you can treat it. So it's one of those things that can be prevented. And the problem is there's not enough people to diagnose it. And this project was specifically targeting India, where they don't have retina experts or people who can diagnose retina images. And they were able to train machine learning model that takes an image of your retina. So that's what you see on the left. And then what it does some processing of the image, and it basically tries to highlight the blood vessels. So you see them highlighted in green here. And it also tried to identify the pressure. So by just looking at the pixels from the image, the algorithm tries to predict the pressure associated with each of those blood vessels. And then those pressure measurements are used to predict whether a person has the problem or not. And this DL algorithm was able to, again, outperform ophthalmologists, professional ophthalmologists. It had an accuracy of 84% of correctly predicting their diabetic retinopathy, and ophthalmologists only had 82%. But again, in this application, it was not the problem of outperforming the human. It was a problem to be at least as good as human. And in cases like India, you have a choice of using algorithm or having no diagnostic whatsoever. Okay, so let's talk about natural language processing, one more application of deep neural networks. And we're going to talk about specific algorithms and business applications. So again, we have a problem of classification. Typical problem is to classify whether a review was negative or positive. So you take a review for your business, and let's say you have a popular business, so you have thousands and thousands of reviews that people have on the web, and you want basically to predict it whether it's positive, label 0, or negative, label 1. Semantic search, so we'll see Google is actually doing semantic search now. So when you type something in the Google, the text query, it would use the semantic search. Question and answer, a lot of the chatbots now used by businesses. Content generation, people try to generate reports or articles, so report generation. Language translation, so when you try to translate from English to French, Google Translate, one example of that. And summarization, so summarization is to take a long piece of text. You basically take a long text and you transform it into a short summary. And you can have machine to do that for you. All right, so you might have seen this Watson playing Jeopardy. It has been around for a while now. I think the first time Watson was played maybe 5 or 6 years ago, and the Watson is basically a machine that takes question as an input and produces answer as an output. So it's basically a question answer machine. And Watson was able to win Jeopardy, one of the Jeopardies, and it was designed by a set of scientists in IBM. Google Assistant. So you tell something to your phone. Siri does the same thing. Alexa does the same thing. So it's a question of problem of converting the sequence of frequencies, which is representation of the human speech, to a text first, okay, and then text will be converted into, so it's speech converted to text, and then you have to take this text and you have to calculate the reply. So it's actually a two-step problem. All right, we're gonna skip this one. So natural language processing, we're gonna talk about this word to vector. So what happens if you have a piece of text, then unlike pixels that have natural numeric representation, you remember pixel is just intensity of the color, and it's a number between 0 and 255. Text doesn't have this natural representation in the form of a number. And before you start analyzing text using deep learning models, you have to convert it into a vector or into a matrix. And one of those ways is this word to vector. And we're going to talk about how a piece of text can be first converted to a sequence of numbers. Or essentially a vector. And then you can use this vector, so you go from text to vector, and then you do deep learning model, and then whatever you want to do, if you want to do the, for example, sentiment analysis, you want to predict positive or negative, you're going to use logistic regression at the very end. All right, but let's